All right, so we finally actually introduced the term big O. We've basically been talking about big O without actually saying the term big O notation. So let's reveal it now. So big O is just a way of formalized fuzzy counting. It allows us to talk in a very formal way about how the runtime of an algorithm grows as the inputs grow. That's it. It's a way of describing the relationship between the input to a function or as it grows and how that changes the runtime of that function, the relationship between the input size and then the time relative to that input. So we don't care about the other details, only the broad trends. So we've already been talking about broad trends. We talked about, okay, as n grows here, in this first solution down here, it doesn't matter. It doesn't impact the time that it takes. But in our second solution, which is confusingly called add up to first, as n grows down here, the runtime also grows in proportion, roughly in a linear 1-to-1 pattern with n. So that is big O, what we've been talking about. We just haven't actually been using the correct label. So here's a bit of scary text. We say that an algorithm is big O of f of n if the number of simple operations the computer has to do is eventually less than a constant times f of n as n increases. It's a bunch of gibberish, really. What it's saying, though, is that there's a bunch of these. I'm just going to put them all out here for now. There's a bunch of options. If you haven't seen this notation, by the way, this just means a function with an input of n and then the output. So we're describing the relationship between the input and then the runtime. So it could be linear, meaning that as n scales, the input, the runtime scales as well, which we've already seen. It could be something different. It could be quadratic, where as n grows, the runtime square is related to the square of n. Or it could be constant, which we've already seen as well. As n grows, it doesn't really have an impact because runtime is always constant, which we simplify down to 1. Or it could be something entirely different, and we'll get to some of these other options later on in the course and later in this section. You can always come back and just think about it as when n grows, as an input grows, what is this chart going to look like? Is it going to grow roughly proportionately with n? Is it going to be constant? If we had a square, it would, be a lot steeper than this. One thing I want to highlight is that when we talk about big O, we're talking about the worst case scenario. So we're talking about basically the upper bound for runtime. So let's revisit our examples from earlier. This first add up to, where we only had 3 operations, and it's constant. It's always 3 operations. So the line we looked at was this one down here that roughly is constant. Remember, in the real world, it's not. It goes up and down a little bit, and runtime does vary, but overall the trend is that it's flat. So we could say that this has a big O of 1, and this is the notation that we'll see. So when you see a big O and then in parentheses, you see 1 or you see n or n squared or n log n or log n, things we haven't gotten to, that is telling us that as n grows, as the input to this function grows, in this case, it has no change. It's not reflected in the runtime. But if we take a look at this one, add up to n, same name, this was the one that had a bunch of operations that are happening where we said that it grows as n grows, the runtime grows, basically in a 1-to-1 ratio. The number of operations is eventually bounded by a multiple of n. It doesn't actually matter if it's 1n or 5n or 50n, because at the end of the day, we simplify it down just to n. And we're going to talk about the rules for simplifying these expressions. But basically, we're concerned with just the order of magnitude. So we don't care if it's 5n or just plain old n. It's the same when we're charting it on a massive chart and we're zooming way out and we're just carrying in a fuzzy way, I guess is what you would say. So here's another example we haven't seen. It's called count up and down. And all that it does, I'll just copy it over. I don't actually have a snippet for it, but let's just plug in 10. Okay, so our output is going up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. At the top, going down 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Back down. All right, so if we were trying to figure out the big O for this function, we'd start by saying, all right, so here, as n grows, we have roughly n operations. We have a loop. So there's big O of n here, because this, as n grows, this loop grows. Same thing down here. As n grows, this loop grows. It's just doing the same thing in the other order, going back down. So you might think that the big N is 2n, but remember that we don't care about that. We care about the big picture, so we simplify it to big O n. So if we go back to our performance tracker, I do have count up and down added in here. So let's plot it out with 100. Let's do 1,000, 10,000. And you'll see, I think that's the last one I'll do. It's taking a while. The next one will take forever. There we go. And you can see there, we get that chart that we discussed. This is the big picture of anything that has big O of n. And we have one more example. And this one's different. We haven't seen this yet. So we have a nested loop. So what it does, it's called print all pairs. And if I plug in 5, it's going to print every pair of the numbers 0 to 5. So it'll be 0, 0, 0, 1, 0, 2, all the way up to 5, 5. And I won't show you the example, but you can trust me, that's what it does. And there's 2 loops. And just like we discussed with the loop, this loop is based off of n, this first one. So that's big O of n, right? As n grows, this is going to be n number of operations, roughly. But then we have a nested loop, which is also the same thing, O of n, which just means that as n grows, this loop, the number of times it runs grows as well. But this is not O of 2n, which simplifies to O of n, because it's nested. And that gives us something else. An O of n operation inside of an O of n operation is O of n squared. So what this means is that as n grows, the runtime roughly grows at the rate of n squared. So that's a pretty significant difference. And if we plot it out, which we will in just a second, you'll see that. But hopefully that makes sense. I don't know why I paused there. Hopefully that makes sense of why there's such a difference. Because if we step through this, if n is, let's just think about the number of pairs. If n is 2, we have the pair 0, 0, we have 0, 1, then we have the pair 1, 0, and 1, 1. So there's 4 pairs. But if we increase n to 3, all of a sudden we have 9 pairs. I won't go through them all, but it increases very quickly. If we increase to 4, we've got 16 pairs. So I said I wouldn't do this, but I added it into my console, print all pairs. If we do 2, there you go, we get the 4 pairs. If we do 3, we get a lot more, 9. Now if we go here and plot this, print all pairs, I'm going to start pretty small and do 10. I'm not even going to go to 100 right away. Let's do 50. Now let's do 100. Let's do 120, 150. All right, so you can see what we're working with here. And I'll try 200. It might take a little while. Okay, I'll leave it at this. This is a different overall trend, a fuzzy version of the chart. We're not looking at a linear thing where as n grows, the runtime is roughly proportionate. It's proportionate to n squared. So as n grows larger, the runtime grows even larger. It grows n times n larger, roughly. And just to show you this, if I increase this to 300, it's going to take a lot longer. And I think I was playing around with 500 earlier, and that was about as much as my computer browser wanted to do at the time. Oh dear. Okay, so there you go. You can see that this, what used to look very steep, now that we've added in 500, that doesn't look so bad, and now it looks really steep, which is the exponential curve. Remember that it's just a generalized way for talking about how efficient an algorithm is. As an input n grows, how does that change or reflect in the runtime? So we've seen a couple of options. We saw add up to first, which was basically big O of n. As n grew, the output, the runtime grew relative to n. Then we had up to second, add up to second, which was constant. It always took roughly the same amount of time. Then we had count up and down, where it was the same as add up to first. If n grows, if it triples, then our runtime is roughly going to triple. And then finally we saw print all pairs, which was our first quadratic, O of n squared, where as n increases, the runtime increases roughly at the rate of n squared. So I'm hoping I didn't lose you there. If I did, well, we have some exercises after this. Hopefully it will help out a little bit. I recommend that you play around with that tool, but be careful, because if you plug in super large numbers, it will take forever and or crash your browser window, and you'll have to quit that window. Just a word of warning.